Hello everyone. In today's video, we are exploring digital image processing basics with a cool project. We have cooked up a MATLAB program that turns input images into different outputs based on the filters we use. But before we jump onto the fun GUI stuff, let's quickly gather the basic knowledge on these filters and what makes them tick. So let's start with the black and white filter. So basically, we are the group members, myself, Avin, Jayesh, Falanshu, Raman, and Krityuk. So the first one is black and white conversion. For converting a color image to black and white, that is grayscale, a common approach is to use the luminosity method or average method. The luminosity method is a color to grayscale conversion technique that aims to represent the intensity or brightness of an image while preserving its perceived luminance. So in this method, basically the intensity of each pixel in the grayscale image is computed as a weighted sum of the original color channels, typically using the formula which is being displayed on the screen as y is equals to 0.299 R plus where R is red color plus 0.587 G which is green plus 0.1414 which is blue. So basically the notations are RGB, the red, green and blue colors. The coefficients are there. The next slide, in the context of this code, the show output histogram function is expected to take an image as input, calculates its pixel intensity distribution, then visualize this distribution in a histogram. Histogram is commonly displayed on a designated UI axis, such as the output histogram axis in this code. As we can see on the screen, the input image is given to the code. After that, it gets converted into black and white. The next slide, which is output histogram, as being displayed on the screen. As we can see, with the intensity increasing, the number of pixels are also increasing in black and white. Then the second filter is sepia filter. The sepia filter does not involve the use of kernel or matrix in the typical sense, as it's not a convolution-based operation like certain image processing filters. Basically, convolution involves applying a filter or kernel to an image. Instead, the sepia filter applies a color transformation directly to each pixel in the RGB image. The transformation is typically achieved through a set of linear operations that modify the intensity values of red, green, and blue channels. In mathematical terms, we can understand it as RGB represent the original red, green, and blue values of a pixel. The sepia transformation might be expressed as follows. The equations are as follows, as being displayed on the screen. Then we can see the input image being given and it's converted after applying the sepia filter. And the corresponding his output histogram is being displayed on the screen. As the intensity is being increasing, the number of pixels of blue color are also increasing, as well as the green and the red, while being the least being the red. Now I would like to give to Jayesh to for the further presentation.
So now let's talk about monochrome. Have you ever seen those stunning photos where everything is bathed in a single vibrant color? Like everything is either the shades of red or blue or green or any other color. Well, that's the magic of monochrome manipulation. We will learn how to achieve this effect, but first let's break it down because there are some many mathematical and other kernels used behind it. So an image is essentially a collection of pixels. Each contains a red, green or blue values, RGB. By manipulating these values, we can alter the image color composition. So how do we achieve this monochrome? So there are several methods. I'm going to teach you each method line by line. So first method is channel selection. So in this method, we just pick one of the RGB channel, like either red, either green or either blue, and discard the other color. If I'm choosing, if I want to make the red monochrome, I will discard the blue and green channels. Okay, so imagine taking a photo with a red filter. Only the red channel gets recorded. This method is easy to understand and implement, but it can sometimes result in the loss of details. Now, the second method is weighted sum method. Now, let's get a bit more mathematical. We can assign weight to each RGB channel and create a new single channel image based on the weighted sum. For example, to create a red dominant image, we might have a higher weight to the red channel and lower weight to the green and blue. This allows more nuanced control over the final color tone. Now method 3, it requires kernel. Kernels and convolution. Here's where things get really cool. Kernels are small matrices used for image processing tasks. We can design a custom kernel that selectively amplifies or suppresses specific color information in the image. Then we perform a mathematical operation called convolution, which essentially slides the kernel across the image and applies its effect at each pixel. This allows for a wide range of creative possibilities, like creating smooth color transition or highlighting specific details. So here is the output of the red monochrome. So you can see that the different colors like blue and green are discarded here. Only the red, you can see the red part of the image. Similarly with blue monochrome, we are discarding the red and green channel. So if you can see the original image, we are extracting all the blue components from it, and the histograms will similarly reflect the all the blue components of the image. Similarly, what we do for green, we discard the red and blue channels. As you can see its histogram, you can see it's only giving us the feedback of green intensities.
So, Namaskaram everyone. I am here to talk about sharpening as a digital image processing technique that enhances the perception of edges and fine details in an image. It is often achieved through convolution, a mathematical operation that involves applying a filter or kernel to each pixel in the image. The Laplacian kernel is a specific convolution kernel commonly used for sharpening, and the basic form of a Laplacian kernel is, as you can see it, 0, -1, 0, -1, 4, -1, 0, -1, 0. This is the matrix. So when this kernel is convolved with an image, it emphasizes rapid changes in intensity, which correspond to edges in the image. The central element reinforces the current pixel's intensity, while the surrounding elements contribute to detecting changes in intensity. Adjusting the weights of the kernel allows for control over the strength of the sharpening effect. By tweaking these values, you can fine-tune how much the edges are enhanced, providing flexibility in achieving the desired level of image sharpening. So this is a output histogram for the after using the sharpening method. As you can see all in this, that after applying the sharpening method, the curve has become smoother, more smoother than it was. The peaks have gone smooth. Next, this is another common image processing technique, which is known as blurring. So blurring is a common image processing technique used to reduce sharpness and detail, creating a smoother or softer appearance. Convolution with a blur kernel is a key method for achieving this effect. The Gaussian blur kernel is a widely used kernel for blurring. Its 3x3 matrix is, as you can see all, this is given in the presentation. Now, when this kernel is convolved with an image, it assigns more weight to the central pixel and gradually decreases the weights as you move away from the center. The distribution mimics the shape of a Gaussian distribution, hence the name. So that's why its name is given. And the purpose is to create a weighted average of neighboring pixel values, resulting in a smooth and blended appearance. By adjusting the size and weights of the Gaussian blur kernel, you can control the degree of blurring. Means by adjusting the size and weights of the Gaussian blur kernel, you can control the degree of blurring. And large kernel sizes and higher weights lead to more pronounced blurring, while small sizes and lower weights produce a subtler effect. So it depends on the user how much of the blurring effect one wants. If one wants more blurring effect, then one can use large kernel sizes and higher weights. If one wants less blurring effect, then one can use less kernel sizes and less weights. Now, this flexibility allows for fine-tuning the level of blurring based on the specific requirements of the image. And this is, as you can see, just quite the opposite of sharpening method, because in the sharpening method, the peaks were removed and they have gone smooth. In this method, there are more peaks than the original image was probably processing with itself. So this is a method which can create more peaks, and this is to create a smoother or softer appearance in the image. In the histogram, it shows more peaks. Now our members will continue the same.
Brightness adjustment method. Brightness adjustment in image processing involves modifying the intensity of each pixel in the image. The adjustment of image is achieved by the formula adjusted pixel value is equal to original pixel value plus the brightness offset. Here the brightness offset is a user-defined parameter that determines the amount of adjustment. If it is positive, then it increases the brightness. If it's negative, then it decreases the brightness. The process iterates through each pixel, ensuring the adjusted value stay within the valid intensity range, that is from 0 to 255 for an 8-bit image, to prevent clipping. This method allows users to control the overall brightness of image by uniformly altering the pixel intensities. Here the output histogram for the brightness change. From the histogram, we can say that the histogram is shifting towards the white side. Now we are going to talk about the age detection. Age detection is a technique used to identify boundaries within an image where significant changes in intensity occur. One commonly used method for age detection is a Sobel operator. Here's a concise explanation for the logic behind age detection using Sobel operator. Age detection using Sobel operator involves the following steps. First one is grayscale conversion and second is gradient calculation. In grayscale conversion, we used to convert an input RGB image to grayscale using the RGB to gray function. This step simplifies the image to a single channel representing intensity. In gradient calculation, we use to apply the Sobel operator to calculate gradient both horizontal and vertical direction. The Sobel operator for horizontal direction is given by the matrices -1, -2, -1, 0, 0, 0, and 1 to 1. The Sobel operator for vertical direction is obtained by transposing the horizontal direction matrices. Convolve the matrices with the grayscale image to obtain the horizontal and vertical gradients. The Sobel operator is effective for detecting is due to sensitivity to intensity variation in both horizontal and vertical directions. Now in output diagram of age detection, here we can see that the histogram is shifting more towards the black side.
Now here comes the inverting colors part, which means that we need to flip the colors. So for this purpose, we need to access all the pixel values, and we would change all the pixel values to its complement. So the formula for it is going to be like color equals to 255 minus original color. And in this way, we are just updating the RGB values of each pixel with their complementary colors. And then we will be displaying the result inverted color image in the designated UI axis. So now this is the image for that. This is the output histogram for this.
So after getting a brief understanding of several filters and their principles behind, now we are ready to implement our knowledge. So here we have created a MATLAB program and GUI which will help us better understand the concepts visually. So what our program do? Let's see its functionalities. First of all, we will take an input image and we will see its histogram. Now, secondly, we will use different filters to process the image, and its respective histogram will be shown in the GUI. So after that, we can save the output to better analyze the output. So this is the interface of MATLAB. As you can see here, we have created the design of the app, or the face of the app, in which you can see there are several radio buttons depicting different filters like black and white, sepia, red, monochrome, and there is a slider through which you can select the intensity of sharpness, blur, or brightness. Also, there is a load custom image button through which you can add your custom image into this app. And after you add this image, the app through its program converts its red, blue, and green intensities and show its histogram in this area. After that, you select any of the filter. The output image, the converted image, will be shown here, and its corresponding histogram will be shown here. And you can save the output in this field. Now you can see the code behind it, in which we have selected, and in which the radio button, there is a callback function through which through which by different fields with different filters there is a specific function running behind it. So let's see how the GUI is working. We will run this program. Okay, so now our GUI is open, and you can see its interface is very cool and genuine. Now we will load an image. Suppose we will select an image from here. This is the original image. Now we will open it. So as you can see, the corresponding red, blue, and green components of the histogram are shown in this field. Now if we select the black sepia, it will turn the image. It will apply on the filter, and the filter will be get applied on the image. Similarly with red, blue, green, and you can also invert color. You can see the corresponding histogram is also activating in this field. So if you want to sharpen the image, you will first select the slider and then sharpen the image. Similarly, you can do for blur, you can do for brightness, and you can do for edge detection. To save this output, you just simply click on the save output button and type the name of the output image and save it. So our input image is converted into the required output image. Well, that's all.